I will give demonstration on how to use MANORAA. So first you go to the URL manora.org, which will be redirect to here. So manora.org. Then the fastest way, you can click on sample. And then you can see this one is for staurosporine. And if you want to change to methotrexate, you can put the PDB3 letter code of the ligand, MTX, like this. And then it will go to methotrexate here. Or you can go to trimethoprim. You can click, put TOP, trimethoprim. So this is top. So it works on any ligand in the PDB with enough structure for superposition. So let's go back to staurosporine. So this one, you can see that these panels is the staurosporine, and these are the atoms that will be used for superposition. So the default is heteroatoms, but if you want to superpose more precisely, you can roughly estimate the core structure of the ligand by clicking on structural conservation. In structural conservation, it will superpose all the structure with that ligand on the list of atoms that you input, and the flexibility of the atoms will normally represent by the yellow color, and then it fade to green to cyan to the most superimposable in blue. So it will be go from spectrum of yellow, green, cyan, and blue. And you can see that these atoms are very well superposed. And then you can proceed with this list of atoms. And you can go to binding distance correlation. If you click here, it will do the atoms that you select in the previous page, and it will superpose all these atom by atoms. So after superposition, it will give you the list of frequently occurring atoms according to the superposition atoms that you input. And these are the residues that are equivalent. And on the header will be the residues that used for distance measurement, such as this one, the distance will be B11, B12, B20. So it's B11, B20. And then this is the influential distance equation. Normally, the most influential distance will give rise to only one distance. So you will have to manually select the atom for superposition and try to minimize the distance parameters to only one most influential distance. And the green color mean contraction, the yellow color mean expansion. So you can see more clearly in this drug design button. So the list of atoms, this one will be still the same, heteroatoms. But if the ligand are flexible, it should be along the rigid core. Flexibility of ligand will be make the superposition very hard to give any meaningful result. So normally it works with rigid core ligand. And then this one gives rise to equation. And if you click on conservation, these are the atoms in the bin that are used for distance measurement. Is the frequently occurring atoms. And these are all the distance measured by these interresidue distances. And if you click on contraction, this is the direction in the pocket that should be contract in order to gain affinity. So this one, the N lobe and C lobe should be closer together in order to get the lower binding affinity. So log Ki very small, that means this distance should be smaller in order to get the log Ki very low. So If this number is small, log Ki is small. And another function would be the pathway discovery and target organs. So this one, if you click on this one, KPCT human, you can see that this is the protein target of staurosporine. You can click on the pathways. This is autophagy pathways. So it will load into the pathways. And this is the protein that is the target of this staurosporine. So staurosporine have many targets. It's very promiscuous, so it gives rise to many pathways and many protein. And if you want to look into the target tissues or organ, you can click on open target. In this open target, if you click to baseline expression, you can see that this autophagy exists in immune organ and in blood and in endocrine gland. And you can also see the affinity. Affinity will be sorted from smallest, which is the tightest binding, to the loosely bound and the non-binding PDB codes. And you can also upload the PDB here. If you have the structure that conform to the PDB format, you can upload your own structure and put the affinity to plot the binding distance correlation. You can also sort the data according to affinity like this. So you can also sort the pathways and target protein and PDB code and resolution like this. And you can filter the residues, the resolution. Another function is protein ligand interaction. By this button, it will show how many hydrogen bond or how many ionic interaction exist with the input set of atoms that you input. So this one, it uses nitrogen, N1, N2, N3, N4, and the 3 oxygen. And if you click on the structure, you can see the hydrogen bond like this. So it will shows the hydrogen bond that this staurosporine and this set of atom made with this particular protein 1XJD. So we find that there is trends of hydrogen bond numbers according to the binding affinities. You can also save it in order to present into your report like this. Thank you.